the University of Chicago. She kept going to Los Alamos, to the mountain zone. And in 2007, she has arrived here at Stanford, and we are very happy about it. We don't know, according to her travel plans, maybe her next stop will be Alaska, and then she wants to retire in Hawaii. But before she does that, she will guide you to a journey to the center of the Earth. Please welcome Wendy Mao.
Thanks a lot, Uwe, for that introduction, and thank you all for coming here tonight. So yes, the title of my talk tonight is Journey to the Center of the Earth, Exploring High Pressure. So our journey starts with this man, French writer Jules Verne. He's also known as the father of science fiction, and he's also the second most translated author, I learned this online, after Agatha Christie. So if you look at Verne's work, it was actually very prescient. So his writings on space, air, and underwater travel were well ahead of their time. And if we look, let's take a look at 4 of his most famous novels with the hindsight that we have due to the fact that we live in the 21st century. So first we look at 20,000 Leagues Under the Sea. This tells the story of Captain Nemo and his submarine, the Nautilus, as it explores the deepest parts of the oceans and also encounters many kind of scary sea monsters. 90 years after the publication of 20,000 Leagues Under the Sea, in 1960, the Trieste, a diving submersible with its crew of 2 men, actually explored the deepest parts in the world's oceans. So this is the Marianas Trench, which is 11 kilometers below sea level. If we look at Around the World in 80 Days, this is the novel that tells the story of Phileas Fogg and his wager of 20,000 pounds in order to circumnavigate the globe in 80 days. And it's a subject of the 1956 Academy Award-winning Best Picture. Also in 2004, it was remade. And probably a lot of you guys know that it also starred our illustrious governor in his last movie role. So if we look at circumnavigation, in 1850, it took about a year to sail around the globe. In the late 19th century, early 20th century, a number of innovations, including the opening of the Suez Canal and the Panama Canal, and also the use of steam propulsion, brought down the number of days to about 60 in 1925. And then, of course, with the introduction of jet planes, it now takes less than a day to go around the world. If we look at the novel From the Earth to the Moon, this tells the story of a Frenchman and two Americans who build a projectile and shoot themselves from the Earth to the Moon. A little bit more than a century later, this fiction became fact, and of course this year we're celebrating the 40th anniversary of the Apollo 11 landing. And then so finally we come to the title of my talk, which is, of course, comes from Verne's novel, Journey to the Center of the Earth. So this tells the story of a group of explorers who travel down a volcanic tube to the center of the Earth, and along the way they encounter more and more prehistoric animals, natural hazards, until they come to the center, which is void space, and then there are also a lot of prehistoric creatures there. So this novel is also the subject of many remakes and film and movie adaptations. The most recent from last year, this I think was also in 3D, shows that the center of the Earth has an underground ocean and many prehistoric dinosaurs and plants. So I'm guessing most people in the audience don't believe that, while this is made for great science fiction, don't believe that the center of the Earth has dinosaurs in it. Well, I hope most of you will. I hope to convince most of you that doesn't include dinosaurs. We'll see if it's convincing or not. But then you might wonder, well, what do we know from science? How do we know what's in the center of the Earth? I mean, we traveled to the moon. How far are we to realizing, or how close are we to realizing a journey to the center of the Earth? So then the question might be, how far down has man gone into the planet? So it's a very long trip to the center of the Earth. The radius of the Earth is 6,371 kilometers. This is almost 4,000 miles. So for comparison, if you want to take a cross-country flight from New York to San Francisco, it's less than the radius of the Earth, 4,000 kilometers. If you look at the deepest mine shaft, the deepest people have dug into the planet, this is the Tautona gold mine in South Africa, and it's 4 kilometers deep. This is quite a remarkable feat of technology, but I mean, 4 kilometers compared to 6,371 kilometers, we're barely scratching the surface of the planet. And at these depths of 4 kilometers, you start to encounter lots of problems. At 4 kilometers, the temperature and the surrounding temperature gets to 60 degrees Celsius. This is 140 degrees Fahrenheit. Very, very hot, so you need massive cooling equipment to keep the mines habitable. Also, the pressures at this depth in the planet are about 900 times higher than at the surface. So very, very high pressures, very, very high temperatures. So it's quite dangerous conditions in mines. And every year, about 250 people die in South African mines. So 4 kilometers, not very much. But what if we scale back our expectations and say we don't have to send a person down there, but let's just see how far we can actually dig a hole or dig a kind of a core into the Earth? Well, the Kola super deep borehole was a Russian scientific drilling project. So this dug 12.3 kilometers into the Kola Peninsula. Again, 12.3 kilometers is more than 4, but still a lot less than 6,371. Beyond these depths, the reason why I couldn't dig deeper is because the rock gets so hot and so soft that immediately as you start digging in, the hole immediately closes. So again, 12.3 kilometers, this is 0.2% of 6,371, so we're 99.8% that you still have to go. So what if we scale back even further? Like, what are the deepest samples we can even hope to get directly from inside the planet? Well, from volcanic eruptions, we can actually get some samples from deeper within the planet. So diamonds, so this outer clear portion, diamonds form deep within the planet, and they can sometimes be brought up rapidly through volcanic eruptions. And within them, they can trap certain minerals that tell us something about what's inside the Earth. So here we have a garnet crystal that's been trapped in a diamond that came from probably a few hundred kilometers within the planet. Okay, so, but still, a few hundred kilometers, not that far down into the Earth. And to just show this graphically, I wanted to use Terry Anderson's very nice graphic to kind of show this again. So if we look at how far to go from the crust down into the core of our planet, 6,371 kilometers, the samples that we get from diamonds or from volcanic eruptions still are barely past the first rung down into the core. And the volume of the Earth that's really sampled, if we think about this 300 kilometers, is only less than 14% of the planet. If we look at how much man has directly with its state-of-the-art technology, how much we've been able to dig, well, now we have to really blow up this one rung of the ladder. And I mean, this is a pretty high resolution figure. I had to blow up so you can now see all the fuzziness, and that's basically where we are with the borehole. So you might at this point say, well, maybe Verne is right? Well, what do we know about the center of the planet? How do we have any observations about what's going on down in this yellow part? Well, our main observations about the Earth's interior come from seismology. So this is the study of earthquakes and the seismic waves they create. So an earthquake occurs when you have 2 blocks of Earth and they suddenly slip past one another. So this releases a large amount of energy that then radiates from the earthquake epicenter in the form of seismic waves. It's kind of like ripples on a pond. So I think in the Bay Area, we're quite sensitive to the power that's released in earthquakes. So this is a picture from Loma Prieta, the earthquake in 1989. So next month we'll be celebrating, well, not celebrating, it will be the 20th anniversary of the Loma Prieta earthquake. And so here's just a picture of where the upper deck of the Bay Bridge actually collapsed because of the devastating power of these earthquakes. But even Loma Prieta is only 3% of the power or the energy that they think was in this great San Francisco earthquake of 1906. So earthquakes are certainly a large concern in terms of a natural hazard, but they also can provide seismologists with a lot of information because the seismic waves they create are our main observation of the Earth's interior. So as these waves travel into the Earth's interior, they interact with the material they're moving through, and then they tell you something about those materials inside the planet. So sort of a reasonable analogy to how seismology works is taken from medical imaging, so ultrasounds or CAT scans. So here you have some sort of energy source that creates waves that then travel through the object of interest, and then the waves can get reflected off of surfaces, or the velocity and the amplitudes of the waves can change. And as you measure what happens to the waves, that tells you something about the material or the structures inside of the object that you're trying to image. So if you take collect a lot of these waves in one direction, but with different depths, now you can see the head and the body of the little baby from the ultrasound. But also if we take a lot of slices with depth in the Earth. So here is just are different slices from Central America and Japan. So this is going down in depth from the surface of the planet down to just above the core. You can see these red sections are areas where the velocities are slower than average, and then these blue regions are regions which are faster than average. And so you can start to image certain structures that are within the planet. And so here in Japan, we actually see the Pacific plate is this blue line here, traveling or subducting, moving under Japan. So it's moving underneath Japan, and then it's sinking into the mantle. If you take enough of these 2D images from different orientations, you can then reconstruct a three-dimensional image of the internal objects. So here again on the left, we have many different views of the baby, and then together we get a pretty reasonable 3D baby reconstructed, right? So good. And then on the right, I show some 3D structures in the Earth. So here, this on top, you might be able to see the white lines show the continents. It shows a little map of the Earth. And then I show with depth down to the core mantle boundary again, so just above the core. And then these big, large red structures are just regions, again, where velocity is a little bit slower. And then these blue regions are where velocity is a little bit faster. And then it's up to seismologists, and seismologists try to reconstruct what does that mean? Like, what do these slow and fast regions mean? What changes the velocity? So it could be structure of the materials, could be temperature, could be composition. So, but we can't image that there are some things going on here. So then, seismology is a relatively young field. Prior to the mid-1800s, really the view of the Earth's interior was largely unconstrained. And so like this picture from the 1600s shows volcanic vents and many underwater geysers that are connected to the surface. And these sort of pictures probably influenced Jules Verne a lot. But then by the 1900s, then you start seeing the layers, and you see a solid or a core that has no voids. That's good. And then as we move to more current times, have a more and more refined picture of the Earth. And then we also see some more local variations. So our picture is continuing to be refined. So now I just want to take you on kind of a average view. So what would happen if we were to go from the surface down to the core? What would we find? So the structure of the Earth is composed of many different layers. Roughly can be thought of as separated between the crust, the mantle, and the core. The crust, this is the layer that we live on, really is a very minor part of the Earth. It's only 0.5% of the Earth. But we have a lot of direct samples of this part of the planet. So it's divided into oceanic and continental crust. So in terms of oceanic crust, this crust is comparatively thin. It's about 5 to 15 kilometers. Also, if we look at the age of the crust, it's pretty young. So it's less than, geologically young, 200 million years. Also, the reason why it's young is it's because it's quite dense. So when an oceanic crust meets continental crust, it always ends up subducting. So it always ends up being recycled back into the mantle. So it's usually never more than 200 million years old. And it's composed of kind of heavier things like magnesium and iron-rich minerals. So a typical oceanic crustal rock is this kind of dark rock called basalt. If we look at the continental crust, in contrast, it's very thick. So it's 30 to 60 kilometers thick. It's also very old, like more than 4 billion years old. And the reason why it's old is because it's quite light, so it very rarely subducts. So it just keeps on collecting and ponding at the surface. And then if we look at a typical continental crustal material is granite. And I think we're all familiar with this. Our kitchen countertops are made of this sort of rock. And it's rich in SiO2. That's what makes it pretty light. Or silicon dioxide. Okay, so that's the crust. We have some direct samples, but really doesn't tell us much about the planet as a whole. The major part of the Earth by weight is the mantle. So this is 70% of the Earth's mass. And it's separated into 3 major layers: the upper mantle, the transition zone, and the lower mantle. So we have a few samples from the upper mantle because, again, volcanoes can bring up some of the material. But largely, the transition zone and lower mantle are untapped. So we don't have direct samples from that. Then how do we know what the rest of the planet is made up of? Well, if we look at a periodic table of elements and look at what are the major elements that make up the planet, so this periodic table is coded so that the elements shown in light blue are present in the Earth more than 2%. The elements in pink are between 0.1 and 2%. And then trace elements are elements that are less than 0.1% in the Earth. So actually the Earth is very simple. It's mainly 5 elements: magnesium, iron, silicon, oxygen, and sulfur barely makes the list of above 2%. And then a few 8 minor elements, and that's about it if you want to take a very rough estimate of the Earth's composition. And then just this pie chart shows, just again, graphically, if you want to know the amounts, that basically the Earth is iron, magnesium, oxygen, silicon. So when you start putting these elements together, you start forming the minerals and rocks that make up the Earth's mantle. So we do have some samples that come from the upper mantle. So this is a chunk of a rock called Ringwoodite, and it's made up of 3 main minerals. This kind of pretty light green mineral is called olivine. So again, remember those characters: magnesium, iron, silicon, oxygen. It also has some pyroxenes. These are the darker green and black minerals: magnesium, iron, silicon, oxygen. And then we have these really pretty red garnets. So we have a little bit of calcium here, but mainly magnesium, iron, some aluminum, silicon, oxygen. But so we have these main building blocks, these main elements we're going to put together. But then what happens inside the Earth? So we know at the surface what sort of chemistries they combine to form. But is that true deeper in the planet? So for that, we need to look at these materials at the conditions that are inside the Earth. So we look at a plot of temperature and pressure conditions inside the Earth. This red block here shows what we think is a reasonable envelope of potential conditions inside the planet. And so temperatures can range from surface temperatures down up to very, very high temperatures, 6,000 degrees Celsius. This is in excess of the temperature at of the surface of the sun. And then in terms of pressures, we can reach over 3.5 million atmospheres. So these are very, very high pressures. And I wanted to discuss, since the title also has exploring high pressure, what do I mean by pressure? To give you kind of a feel of when we say like 3 million sounds like a lot, but what does that mean? So what is pressure? Well, pressure is defined as force per unit area. So in the Earth, when we think about pressure, a good reference point is the pressure at sea level, and that's 1 atmosphere. So that's basically the weight of the air column above the surface. So it's equal to 1 atmosphere. Of course, if you move higher in elevation, so like the top of Mount Everest, then you have less of an air column above you, right? So now the pressure at Mount Everest is lower, so you have less force on you. So it's only 1/4 of an atmosphere. If instead you go deeper into the planet, so if you take an underwater dive, so the deepest scuba dive, 318 meters, now you have the weight of the water, plus you have the air column, and the pressures become quite high, 32 atmospheres. So 32 times the pressure you see on the surface of the planet. And then if you go to the bottom of the Marianas Trench, so the deepest part of the Earth's ocean, you have 1,000 times higher pressure than at sea level. So when pressure starts increasing, if you look at this formula, pressure increases if you either increase force or decrease area. So we'll be using that to our advantage. So to show this kind of in pictures, if we think about, okay, so we can increase force by making something much heavier, right? So we think about an African elephant, typically about 10,000 pounds. And okay, so let's think about this elephant as being very acrobatic. So if it can balance on just 1 foot, then the area is about 260 centimeters squared. If you look at how much pressure that 1 foot would put on you, it'd be 10 atmospheres. I think that's actually surprisingly low. I was surprised I did the calculation, but 10 atmospheres, I checked this. So if instead we look at what's the effect of decreasing area, if we take like a pretty petite person, 100 pounds, and then we balance it on the tip of a very small stiletto heel, so say half a centimeter squared, it's actually 10 times the pressure. So it hurts, it hurts a lot to get stepped on by stilettos. Okay, good. But so it shows that, okay, of course you can increase pressure by increasing force or decreasing area. Okay. Oh, so then I say, so but why do we care? So I've discussed pressure. Why do we care about the effect of pressure and temperature or these conditions? Like, what effect does that have on materials? Let's look at a material that we're all pretty familiar with, water, H2O. So we know the effect of temperature, and we experience the effect of temperature on water every day, right? Sorry. If we go to higher temperature, so above 100 degrees Celsius, we form gas, form vapor. If we cool it below 0 degrees Celsius, we form ice. So we're very familiar with these three quite different phases of water at 1 atmosphere. So here already we can see that somehow pressure starts changing what kind of phases you're going to see. Right? So then if we look at Mount Everest, so if you go to higher altitudes, the effect is you can start boiling water at much lower temperatures. So at 70 degrees Celsius, you actually start boiling water if you're at Mount Everest. But in the Earth, these are still very, very low pressures. And we're talking about 3 million atmospheres before. So so let's see what happens when you start looking further along in this pressure regime to the H2O phase diagram. So adding this pressure dimension actually greatly increases the complexity and richness of this phase diagram. So here again, I applied temperature on the left. But here, in order to show this very wide range of pressures, I'm actually plotting it on what's called a logarithmic scale. So every additional division is 10 times more than the previous one. So this just allows me to plot a very wide range of pressures on a reasonable axis. So here, now when we're adding pressure, we have increased the number of forms of how the H2O can organize itself. So we have actually 20 different known forms of H2O that have been discovered. So this kind of simple molecule H2O actually has very, very rich number of different phases that have quite different properties. And they're changed because of the pressure and temperature conditions. And so I'll just mention also, briefly, maybe some of you guys have heard of Kurt Vonnegut's book, Cat's Cradle. So he describes in that book one particular phase of ice called Ice 9. So it has some sort of literary value. It doesn't have the same properties as Kurt Vonnegut described, but it does exist, so it's been discovered in the lab. So then one question might be, so how do we explore this very wide range of pressures and temperatures? So in my lab, how we've been exploring high pressure is using an instrument called the diamond anvil cell. So a diamond anvil cell operates under a very straightforward principle. So you take the tips of two gem quality diamonds, you just cut off the tips, and then you can squeeze a sample within a gasket. And since pressure is force per unit area, you can generate very, very, very high pressures on the very small area on the sample. So typically the sample chamber is about the diameter of a human hair, so it's about a tenth of a millimeter. But you can generate pressures from up to 5 million atmospheres. So, and just to give you another, just to let you know how much force, it's not too much force. So if you look at the area in the sample, if you apply 230 pounds of force, you get 1 million atmospheres. And then you can go to, at the same time as you're at high pressure, you can change temperature. So you can put the whole cell into a cryostat, into a low temperature device, or you can heat the sample using laser heating or resistive heating, and you can get to very, very high temperatures. So with this diamond anvil cell, so plotting again the conditions within our planet, you can cover a large fraction of the conditions in the Earth. So we can cover the whole mantle and a lot of the core. But we still haven't reached the innermost part of the core. We're getting there. Okay. And diamonds also have the benefit of besides being the strongest material, you want a very strong material to go to these very high pressures, they also are good windows, so they're transparent to a wide range of different probes, because when you're at high pressure and variable temperature, you want to be able to measure the properties, like how the material is changing. So you want it to have a good window material, so you actually look through the diamonds and see how the material is changing. Oh, yeah.
How is it that if the diamond Anvil can reach up to 5,000 degrees Celsius, why is it that it doesn't burn away? Because I read that diamonds can burn.
Yeah. Well, yeah, so that's true at ambient conditions, because at ambient conditions it would burn. But at higher pressure, you can go to higher temperature before it will convert back to graphite. And that, again, has to do with the phase boundaries. So at these very high pressures, you need very, very high temperatures to go back to graphite. Okay, so diamonds make very good windows because you want to probe what's going on. It can be very complicated, the behavior inside the sample. So this is, so often when we have these samples at these very extreme pressures and variable temperatures, we have to use many different in situ probes and integrate them together in order to describe what's going on. So a good analogy is the story of the blind man and the elephant. So a group of blind men were trying to describe what an elephant was like. So one touched the elephant's side and said, oh, an elephant's like a big stone wall. Another touched the elephant's legs and said, oh, an elephant is like the trunks of thick trees. One touched the elephant's tail and said, oh, an elephant's like a rope. One touched the elephant's ear and said an elephant's like a fan. One touched the tusk and said it's like a spear. And one touched the elephant's trunk and said, oh, an elephant's like a snake. So individually, these observations don't give you a good picture of an elephant, right? But when you take them all together, then actually you start to get a pretty accurate picture of what an elephant looks like. And so that's kind of the same way with our diamond cell samples. We want to put together as many observations as we can because we want to have an accurate picture of our little elephant here. So we use laser techniques, electrical and magnetic techniques, neutrons, and also a large number of X-ray techniques. I definitely wanted to highlight this X-ray part because 1/2 of my appointment is in the photon science department. So I do a lot of experiments with X-rays and they couple quite well with our diamond cell samples. So here at SLAC, we have the Stanford synchrotron radiation light source. So this is a facility that produces very bright and small beams of X-rays. And so the small and bright beams couple very well with our very small diamond cell samples. And then there's also many different X-ray probes that have been developed to look at the diamond cell samples. So here is just a little picture. We're using X-ray microscope, and we get a very small aluminum oxide sphere. This is actually a ruby sphere. The size of the sphere is about 1/100 of a millimeter, so it's about the size of an amoeba. And so at 10 atmospheres, it's still a nice round sphere. When we get to 180,000 atmospheres, it's not as well defined because it's kind of squashed. So pressure is making it smaller and it's deforming the shape. And here I just want to say that actually at SSRL you get really great service. So this is Piero Pianetta. He's actually the director of the Stanford synchrotron radiation light source, and he actually came and helped me with my experiment. So really appreciated that. Okay, so getting back to our story about the journey to the center of the Earth. So now we know the materials I think make up most of the planet, and we can reach the conditions, mimic the conditions that are in the planet. So let's just see what happens when we start compressing and heating things. So first we'll discuss this first layer, the upper mantle. And to kind of simplify the picture, we'll look at the major mineral in the mantle. So this is this mineral olivine, so it's this light green mineral here, magnesium, iron to silicon O4. So let's see what happens when we compress this mineral. It represents about 60% of the upper mantle. So we put the sample between the diamonds in the gasket. So here you can see looking down through the diamonds. This is the gasket area, and then this is our little small sample, a 1/10 of a millimeter in diameter. And then at the same time, we can laser heat the sample. So we can use infrared lasers to actually heat our sample to high temperatures. So here, again, this is the sample chamber. So this is where our olivine sample is. And then at high temperature, it's actually starting to glow. So at 1,500 degrees Celsius, you can see it's getting quite hot. And then at the same time, so we're at high pressure, high temperature, we can then use our synchrotron X-ray beam to probe that high pressure, high temperature area. And so we can measure things like the structure of the material. Okay, so if we take olivine, this is the phase that's stable from ambient pressure down to 140,000 atmospheres. This is its structure. So this just means that this just shows from the diagram how the different elements organize in a periodic solid. So these oxygens are shown in red. Within these blue pyramids, you have the silicons, and then within these orange, what we call octahedrons, are magnesium and irons. So this is stable down to 410 kilometers. Oops. So then once you get past 410, something interesting happens to the structure of olivine. So 410 to 670 kilometers, we see a couple of changes in the way that the atoms organize themselves. So first, this material transforms to wadzooite. So you can just see in kind of a general way that definitely the packing is different than before. And the packing is more efficient, so it's 8% higher density because things are getting compressed. So this is a more compressed phase. And this phase is stable from 140,000 to 190,000 atmospheres, so around 110 kilometers thickness. So then this mineral wadzooite then transforms again to another form, all the same formula. So it's all the same elements and the same ratios. And then this new form, Ringwoodite, a little bit more compressed, and 190,000, 240,000 atmospheres, and it's stable for about 140 kilometers. Okay. And then finally we get to the last section of our mantle. This is the largest region, from 670 down to 2,900 kilometers. So what happens to Ringwoodite? So the major transition that separates the transition zone from the lower mantle is that our Ringwoodite decomposes into two different phases. So this is a material called that magnesium, iron, silicon, oxygen 3. It has what's called a perovskite structure. Not too important to know that, but just you can see again, the packing is different. And now actually the silicons, they used to be bonded to 4 different oxygens. Now they're bonded to 6. And that increases the density quite appreciably. But this phase is stable for a very long time. So from 240,000 to over 1.25 million atmospheres. So thousands of kilometers. But to match the chemistry, we also then have to have an oxide phase. So this thing called ferropericlase. And it's just magnesium, iron, oxygen, no silicon. And then very finally, so just before the core, we get one more small transition. So this perovskite phase then transforms to a very creatively titled post-perovskite phase. And this one is only is stable from 1.25 million to 1.34 million atmospheres. So just a little bit over 150 kilometers. And this is actually only discovered very recently. So a group in Japan discovered this new phase in 2004, so five years ago. And the reason why is because it's such high pressures. It's very hard from our diamond Anvil cell techniques to get to these high pressures and high temperatures. So only 5 years ago we knew that this extra transition occurred. And this material actually made up about half of my graduate thesis. So the timing was about right for the discovery and my research. The other half of my, sorry.
What's the time interval involved here?
Yeah. So in our experiments, it happens instantly. In the Earth, there may be, as it's transitioning, it's hard to say. So there could be a lot of kinetics involved. But for our very small samples, the reactions occur instantaneously. Yes.
Also curious about the rarity of the post-perovskite at those depths.
Mm-hmm.
Perhaps silicon, oxygen, and olivine could come back to the surface instead of stay down in the mineral.
Oh, so at these very, very high pressures, they always have to form a solid phase. So this is the stable phase of the silicon and oxygen. They don't move out of that.
If there's just not even as much silicon oxygen going into a mineral like that.
Yeah, so there are some questions out. So you have to have the assumption that when I'm telling you about the average composition of the Earth is correct. There are some people who say there may be a little bit more silicon or less silicon, more oxygen, less oxygen. So that's a big question for geochemistry, like how we know what's in the Earth. Also, silicon and oxygen could go into the Earth's core, actually. So there could be more or less of this material, but we think there's another reason why we think that this material exists, because if we look at its properties, it matches what's observed from the seismic observations. So I should emphasize that too. We always go back, like this 2% density it matches what's observed from seismic observation. So they actually couple really well. Without the observations from seismology, we really couldn't say, we could do all the transitions we wanted in the lab, but they don't mean anything if we're not matching them to what's observed in the Earth. But if you want to say, like, if it's 80% versus 85%, definitely within that level, there could be.
Wait, let me suggest to hold on to your questions to then. We have a long session with questions.
Okay. But yeah, save these. These are good. All right. So the other half of my thesis was discussing the Earth's core, so the deepest part of the planet. This is about a third of the Earth by mass. So here too, the Earth's core is a very remote, very strange part of the planet. So you can have all sorts of different science fiction about what's going on in here. But what scientists have kind of honed in on is that the Earth's core is primarily iron. And it's primarily iron because we don't have any samples, of course, from the Earth's core. We have no hope to ever have those. We think that it's primarily iron for mainly 3 lines of reasoning. One is we need to have an abundant heavy element, so iron fits that bill. Also, the Earth has a magnetic field, and it's generated in an outer core, which is fluid. So you need to have a conducting fluid. So again, iron fits this. And then if we look at the high-pressure experiments on iron, they showed that the composition must be near iron. So it has to match the seismic observations. And then finally, so the core is actually divided into 2 different layers. The outer core, which is liquid, that's mainly iron, a little bit of nickel, and then some of this light element. So some silicon and oxygen are probably in the core. And then there's at the very center, there's a little nugget of solid iron. And this is solid, mainly iron, plus a little bit of nickel. And initially, the core was completely molten. But as the Earth has been cooling, the inner core has actually been growing. And so here I just show again that even though you have, it's mainly just iron, you have these iron atoms, they can pack themselves in different ways. So a lot of research is also going into understanding the phase in the inner core, like how the irons pack themselves. And then this is an increasingly challenging experiment because you need to go to millions and millions of atmospheres and pressure. So that basically is kind of the first order travel through the planet. Of course, there's a lot more refinement and a lot more complexity as you look in this, either in local areas or as you look closer at each of these different layers. But generally, we have a pretty well-constrained picture of what's inside our planet from both the laboratory and from the seismic observations. And I want to say that even if we look even more broadly, there's a lot of other journeys and pressure that one can think of. So if we look at a range of pressures in the Earth, so again, this is plotted on a logarithmic scale because there's just such a large range of pressures that we can experience on our planet. If we look at 1 atmosphere, so that's sea level, center of the Earth, 3.6 million atmospheres. We can also go to very low pressures. So Uwe mentioned that 2 months from now, there will be a talk on the LCLS. So this is the X-ray laser that they've built at SLAC. It'll be the world's brightest X-ray source. It'll produce really short, really bright pulses. So it should be a very exciting machine. But also in the electron gun, so one portion of the LCLS, they have to have very, very low vacuums. So you have pressures of less than a trillionth of an atmosphere. So this is an 8 with 12 zeros in front of it. But even this range of pressures is just a fraction of the range of pressures in our universe, from extremely high pressures at the center of neutron stars to very, very low pressures in galactic space. So I think there'll still be a lot of research for me to do in terms of trying to explore these wide ranges of pressure. So, I mean, exploring pressure, one major application is trying to understand Earth and planetary interiors. But also, I've been recently focusing on how can we use high-pressure studies for practical applications. So some of the information we learn at high pressure can actually be useful for maybe practical materials. So there's been a lot of interest in using hydrogen as a kind of clean energy carrier. But one of the main obstacles to realizing this use of hydrogen in cars is finding a practical hydrogen storage material. So you want to have something, so this is something where actually we found that high pressure studies can provide some guidance for possibly making better hydrogen storage materials. And so these are things that would have very high hydrogen content. Also, you want to be able to make them and store them at near room pressure, room temperature. Also, you want to be able to release the hydrogen easily. You want to be friendly to the environment, also cost, availability, safety are issues. So currently there's no material that fulfills all these requirements. So one type of material we were actually looking at, where we got some guidance from high pressure, are these materials called clathrates. So these are crystals, and they're based on an ice cage. So you have water molecules. They're actually forming cages, cages around different gas molecules. So here we have water forming a cage around this carbon H4, so it's methane. And so it's called a methane clathrate. Clathrates are actually very prevalent in our planet. They represent a very big problem in oil and gas pipelines, because generally clathrates, because they're like ices, they form either at some pressure or low temperature, and they form where you have water and natural gas. So it's almost a perfect mix in an oil pipeline. You have gas, you have water, you have pressure, low temperature. So here's this enormous methane clathrate plug that's formed in a pipeline. You can imagine that this would be a big problem if you're trying to get gas or oil through this pipeline. You have to remove them. So a lot of research goes into trying to not make these materials. But they also just naturally form in our planet. So they form, again, where you have some pressure, low temperature, natural gas, plus water. So this occurs at continental margins, at the edges of the continents, also in permafrost regions. And so here, we're at the Gulf of Mexico. This yellow stuff here is actually methane clathrate, a deposit. And you might be able to see these little pink things in these holes. So there's a blow-up of one of these critters. So it's actually what's called a methane iceworm. So these worms live off of the bacteria that live off the methane in the clathrate. And so methane clathrate might be the most abundant form of hydrocarbon in the Earth. So you might start to think, well, actually, methane, that's a pretty reasonable energy source, right? If you took a chunk of this methane ice, as it melts, all you'd have is water, and you can burn the methane, right? So you actually show, this is a pretty brave person, right? He's holding the methane ice, and it's melting, he's burning it as burning the methane, and then you just have water. That's the byproduct. And so people have tried to, there's been some research that's gone into trying to recover some of the methane from these clathrates. So here's a test well. This is in Canada's Northwest Territories, and this flare is burning off from the methane that's being created from melting the methane ice below. So instead of methane, we thought, well, what if, can you create a hydrogen clathrate? So can we put hydrogen in these cages? So here I show some pictures looking into our diamond anvil cell. And so there's actually two regions in the diamond cell. There's a hydrogen region and a water region. So here are 4 different pictures. They're all taken at high pressure at 3,000 atmospheres. This one on top is at minus 23 degrees centigrade. So here, the hydrogen and water are still separated. They haven't reacted yet. But immediately when we cooled it 1 more degree, we all of a sudden started forming a new phase. So this clear region is the new hydrogen clathrate. And then this dark region is where hydrogen and water are reacting. So they're forming little crystals. And this darkened region is this reactive portion. You can see as time goes on, this clathrate region is continuing to grow. And then you have less and less unreacted part. Finally, at the end of 30 minutes, we have completely formed hydrogen clathrate. And we still have some excess hydrogen in our sample. And then what we found was in this hydrogen clathrate, we have 1 hydrogen for 2 water molecules. So this is a pretty attractive material because if you burned off the hydrogen, all you're left with is water. It's a cheap, environmentally friendly material. And then so we thought, well, let's look at some other simple systems. What about hydrogen and methane? So hydrogen and methane actually starts at high pressure, also forms a lot of different compounds, or a lot of different crystals. So it forms one very hydrogen-rich material. This is 1 methane per 4 hydrogen molecules. This is 33.4 weight percent hydrogen. It's a huge amount of hydrogen storage. And then you can also burn the methane as a secondary fuel. And so here again, you look at the diamond cell sample, you can see these hydrogen, 1 methane, 4 hydrogen molecules growing out of a mixture of 4-to-1 ratio of 1 methane, 4 hydrogen. And then here's just a little schematic showing the structure. Okay, so why are we excited about these? But you do need high pressure to form these. So why are we excited about these materials? Well, let's look at their hydrogen storage capacity. So here I'm just plotting on the left. It shows how much by volume is hydrogen in a particular material. And then on this axis, I'm showing by weight. So really what you want is something that has a lot by weight hydrogen, also by volume hydrogen. And these little red stars show where the Department of Energy wants as target goals for different years for their hydrogen, onboard hydrogen storage systems. So these ellipses here show some more traditional hydrogen, well, actually, some other hydrogen storage materials that have been studied a little bit more than our new high-pressure materials. But you can see this methane 4 hydrogen material has a huge amount, both by weight and by volume. So if we could somehow bring it to more reasonable conditions, we could lower the pressure or increase the temperature, then we would really start talking about this being a potential practical hydrogen storage material. And so we do have some ideas about how we can do that, and I'd be happy to talk to you about that afterwards. Okay, so very finally, I just wanted to end with a little anecdote saying that, well, actually, the ancients also knew a lot about the power of high pressure. So I just got back from a trip to China, so I was reminded of one of the most famous novels in Chinese history is this novel called Journey to the West. And it tells a story of a monk and his disciples as they travel to India to try to recover some Buddhist scriptures. So one of the monk's disciples is this character, Sun Wukong. He's called the Monkey King. And he has a lot of magical abilities and special powers, but he's also very mischievous and rebellious. So in one episode, he gets the deities in heaven really, really angry. So they put him into a special crucible, and they fill it with all these special chemicals. And they cook him for 49 days in an effort to kind of subdue him. By the end of 49 days, they open up the lid, and out jumps the Monkey King. And nothing's happened to him. Only his eyes are now bright red, and they're permanently red. But he's actually more uncontrollable than ever after escaping the crucible. So at this point, Buddha himself has to actually intervene. So the only way to contain the Monkey King is actually by trapping him under the weight of a gigantic mountain. So I think one of the lessons that we can probably learn from this story is that sometimes chemistry and temperature aren't enough, but pressure can be needed. So thank you very much for your attention.
Well, thank you very much, Wendy, and I will open now the forum for questions.
A couple of questions. One is that the process of rearranging the crystals as the pressure increases, is that process reversible in the other direction?
So if you waited enough time, then it should always be reversible. But actually, that's a really good point. So if you're wondering for one of the ways that you could try to trap some materials is that some materials, even once you form them, they can be what's called metastable. So they can exist outside of what they should be stable at. So a good example is diamond. On the surface of the planet, diamond should not exist. It should be graphite. That's how carbon should be. But because of it's very hard to reorganize all the carbon atoms back into graphite. You can keep diamonds. People wear them. We use them in our experiments. But if you were to heat diamond at high temperatures, at low pressures, you would convert back to graphite.
And then the second question is, in the center of the Earth, there's also the radioactive elements, uranium, thorium, and potassium that generate the center of the Earth. Where does that fit in with all the other stuff that you just
So that's very important for the Earth's heat budget, but in terms of the abundance, it's very, very low. So it's kind of trace element. So, but if you want to, of course, understand the Earth, its dynamics, how it evolved, and the thermal evolution, you definitely need to consider radioactivity. And also reactivity is important for understanding the age of the Earth. That's how we determine the age, by the radioactive decay. So it's very important, but in terms of the first order picture for composition, it's not important.
So where does the radioactive elements exist? Is it in the inner core?
So you get concentrations of uranium and thorium in certain crustal elements, because usually when we think of uranium and thorium, actually they don't like to go into the metallic phase, so into the core phase. Lead does. So the product of uranium and thorium decay goes into the core. But uranium and thorium itself shouldn't be concentrated too much in the core. Potassium might be. But it also depends on at high pressure, which hasn't been studied very well. Maybe uranium and thorium at very high pressure would go into the core. And that's something that's actually a very hot topic in geochemistry, like trying to understand at very high pressures, some of our ideas at low pressure change. So how the elements move could be different.
What are some of the challenges you face in this line of experimentation using the lamp and anvil and achieving higher pressures? Why does it take so
Well, you break a lot of diamonds. That's one thing. When you do any experiment above 1 million atmospheres, you start breaking a lot of diamonds. So I'll tell you, for the post-Perovskite experiments that were my graduate thesis, I have broken 100 diamonds so far for that one experiment, which in the grand scheme of things is not, I mean, diamonds aren't that expensive. They're maybe $1,000, $1,500 a piece, but you have to write grants. You have to get money for that, right? So I mean, you don't want to break. So at these very, very high pressures, you often break diamonds. And when you couple high temperature, it's difficult. So if you're going a lower pressure range, 250,000 below, that's pretty reasonable for doing a lot of experiments. And also, very recently, there's a lot of new techniques that come online to probe what's going on. So with all these synchrotron methods, that we now can measure a lot more properties. So we can go to higher pressures, and we can probe more properties. But so question was, why is the Earth's core cooling? Well, why is the Earth's core cooling, and what was the second part? In solidifying. There's a second part. Okay, so and how would that affect the magnetic field? So the reason why the whole planet is cooling. So initially it started with a very hot state when it accreted. When all the little particles came together to form the large planet, there's a lot of energy that transformed from the kinetic energy and potential energy to this one big solid. So the Earth was initially very, very high, much higher temperature than it is now. So it's just been cooling over time. And finally, at some point, you cross the boundary between liquid and solid for iron. And that's the boundary between the outer core and the inner core. So as you cool more, then the inner core keeps on growing. So yeah, if the entire core were to solidify, we'd probably have a problem, because our magnetic field, which protects us from a lot of these cosmic rays and a lot of outside problems, it would be a problem. But it would be, I'm sure people calculate it's probably billions and billions of years from now. It might take longer than when the sun dies.
So you had so have you done? You can go up to 5 million atmospheres, right? So you can get to core pressures.
Mm-hmm.
But all your samples were all about mantle.
Yeah. So again, that's the highest one that's ever been reported. I think you can get to over 1 million atmospheres pretty reasonably if you're willing to break diamonds. But to get to really, really high pressures, like the 5 million, that's reported, in one paper. So that's not something that you can do routinely. And then, and also the reason you might have looked at the graph why I don't have it up. The large box didn't cover the whole Earth, because I mentioned you can get to 5 million, so you get to the core. You can also go to high temperature. You can't do those together. So you can't just get to 5 million plus very, very high temperatures. You kind of have to, if you want to go to very, very high pressures, usually you don't go to also very high temperatures. There's some trade-off there as well.
You had a slide with iron in 3 different states.
Mm-hmm.
The first was body-centered,
Mm.
face-centered cube.
Oh,
What was
okay.
the third one?
Oh, it's hexagonal, close-packed. It's called hexagonal close-packed. So this is just one section of a hexagon.
Okay.
Yeah, it's pretty good. They held it.
So we have, let me mix up a little bit. Let's do one in the back. Yeah.
So the techniques you talked about are ways that you're studying sort of these 5 common elements using the pressure things as well as seismology. Are there people that are trying to study the distributions of the more trace elements in the core and mantle, and how do they do that?
So yeah, geochemists all the time are basically studying that, because how these different trace elements move tell you a lot about the Earth's evolution, and they give you a lot of information about what's going on in the planet. And so that's a whole other suite of instruments. So you need something very high resolution instruments that can tell you elemental abundances with parts per million, parts per billion sometimes. And so there's a lot of instruments on campus. We have a whole.
But how do you do that for the core and the mantle?
So it's much more challenging for our experiment. So if you wanted to take our sample from our diamond anvil cell, we have basically what's a nanogram sample, so 10 to the minus 9. So a billionth of a gram of material. It's very hard to do trace element analysis work on such a small sample. So that kind of limits a lot of the studies for doing really highly precise experiments on trace elements to kind of upper mantle range, because you need larger samples.
Yeah.
Oh.
If you move back 4 billion years
Mhm.
and you try to imagine what happened at that time, why is it that there were only, the elements, the composition basically didn't change, maybe the mix or the phases changed. But if you went back 4 billion years, why were there only these 4 or 5 elements aggregating at that time? What's the reason? Does anybody understand that?
Well, I mean, in order to determine the average abundance, that's another question for geochemistry. So we know, well, we think we know the overall solar abundance, I mean the solar system abundance, because we can look at things like meteorites and like the sun, which kind of give us an average composition of the whole solar system. And then we think we know that at certain time, where the Earth is located, it has a certain, it would have a certain temperature, it's a certain proximity to the sun. So it would be able to accrete, or it would be able to gather certain elements. It wouldn't be able to gather the elements that have very low boiling points. So things like gases, like hydrogen, helium, argon, those aren't very abundant in the planet because they wouldn't solidify. But things like iron, magnesium, silicon, oxygen, they can form these kind of rocks and minerals that, and they're abundant, and they can form at reasonable conditions. So then you look at the overall abundances you think are in the solar system, you look at the conditions you think were occurring when the Earth was formed, and then you come up with these.
But the assumption is that everything, all these elements must have come from supernovas.
Or they came, initially when when our solar system formed, they came from this accreting disk that most of the mass went to the sun. So we look at the sun to get an idea of the solar system composition. But there's a big assumption here that it's kind of homogeneous, right? So we don't know that necessarily where the Earth formed was kind of an average composition that was similar to what the sun is now. And then also we look at little rocks that fall to the planet, and we think that maybe those represent some average composition. But so I think force order we know, but if you want to, argue about some of the minor trace elements, then could be a lot of.
So let me do 3 more questions, and then we can meet for refreshments, and Wendy's also here. So I saw you now, if one row before, yes. No, sorry. Yeah.
Okay, I have a question. Are there any interesting emergent behavior or emergent phenomena that you observe on various compounds at either high pressure or temperature?
Yeah, so are there any emerging novel behavior that you observed at high pressure?
Well, I know strong emergence of wave bursts.
That was strong. I didn't hear that.
How the molecules organize themselves, if they promote behavioral kind of emergence.
Yeah, well, there actually is a lot of pressure. You can imagine it's just like a tuning mechanism. What happens when you bring these atoms closer together? You'll start having the electrons will start interacting very strongly. You can start getting some very interesting behavior. So I just want to show one slide. Oh, where is that one? So let's look at this element here, hydrogen. Why is it, you might know that the periodic table is kind of organized in columns according to properties. So all the elements in this column on the left, this is called the alkali metal column, they're all metallic. But hydrogen is here too, but it's not a metal, it's a gas, right? So it's predicted that high enough pressure, hydrogen will turn into a metal, and also will be a superconducting metal and room temperature superconductor. So it'll have some really strange effects. And a lot of actually elements, when you start compressing them enough, they become metals. A lot of them become superconductors. So that's just one area that people are interested in understanding some fundamental physics. But really, every material you can imagine, just like temperature, you change temperature, you get all these different phases, all the different organizations. Same with pressure. You change how the atoms will organize themselves to have the lowest energy. And then you have sort of novel phenomena, novel behavior, novel structures.
So I saw one more here. Yeah.
What do you use for a gasket material, and how do you keep it from flowing into the sample?
So we do want it to flow, actually. That's a good. It does flow.
Can you repeat the question, please?
Oh, okay. So what kind of materials are used for a gasket material, and how do you prevent it from flowing into the sample, right? Okay, so for the gasket, you want something that's actually going to flow because you want it to support your diamond. So you want the gasket actually supports the entire pressure gradient. At the edge of the gasket, there's no pressure. At the center, there's very, very high pressures. If we just compress this very large, thick gasket, then it would just collapse into the sample. So we actually first compress the gasket so it's very thin between the diamonds, and it's already done its flowing, and then we cut out the sample chamber. So we actually form the shape we want. But it would be, that is exactly what happens.
And what do you use for a material?
Oh, sorry. So we use things like stainless steel, rhenium if we want something stronger. There's some measurements we actually measure through our gasket. So we want something that's X-ray transparent. We use something like beryllium. Almost any metal that has some flow will work.
Okay, last question.
Yeah. Could you comment on implosion techniques? Can't you get, I know it's going to be transient, can't you get higher pressure using implosions?
Yes. So to get to the, so,
Can you repeat?
oh, sorry, explosion, right? So explosions, like, can't you get to much higher pressures? So like nuclear explosions, you can get to like millions of atmospheres for a very, very short period of time, of course, right? So if we want to really measure a lot of properties, then we have to measure on the have to have measurements that can go microseconds or shorter. So that's something where this LCLS might come in handy, because you can have a very bright pulse of X-rays, very short period of time. So that would couple very well with what are called dynamic compression experiments. Usually you don't do explosions in the lab, but we have something like where you can have a gun that shoots a projectile and hits a sample. And you can create very, very high pressures, also very high temperatures for a very short period of time. But previously it was limited because you couldn't have as many probes to measure it. But maybe with these very short pulses of bright X-rays, you can actually do a lot of, that's a one way to go to much higher pressures and temperatures.
Okay, so please let's thank Wendy again.
Thank you.
Please feel free to come down, talk to her, and go outside and have some cookies and coffee.